in image enhancement, and we said the image enhancement, the image after enhancement is, we need a transformation of the image before enhancement, right? So this is how we are doing it. In other words, this t is a function. So we need to define a function that when I give 1 pixel in here, I put it inside my function, I do the calculation, and it tells me that the new pixel value is this. Like I give the pixel value 10, it does the operation, says that 10 is actually 0, or 10 is actually 35. So you find a new pixel value that you need to represent. Now this function is a mathematical function. In other words, you have the freedom of choosing whatever the mathematical function is in your hand, as far as they are leading you to the point that you want to be. So it means that you can have one function, or you can have series of functions. Have you heard of the word piecewise functions? A function which you define different pieces, different functions, so it's a combinational series of functions. So we can do that one. How we find out which function do we need to use? You look at your application. Maybe you will see that, well, you don't really have much of the pixels which are very low or very high, and you have lots of concentration between pixel 11 till pixel, I don't know, 40. So it's very important for you to scratch that part further. The other ones are not much of importance, so you don't have too much. So you don't need to scratch them as much as you do on the rest. So you can define different type of functions. So you need to look at your problem to come up with the very good solutions. That's why that if you read that some scientific papers, you see that there exists some method, let's say, which is very good for some specific medical images. And if you apply for some other images, you don't get a very, very reasonably good results, because it has been defined, the functions, the transformation have been designed for those type of application. Now here, we are seeing two different functions which we want to discuss. We have two transformation functions. Let's discuss about this one, which is a very nice, a very famous function. Now, what happens, how do we read this type of function is this. The x-axis is the old pixel value, and the y-axis is the new pixel value. Let me have a pointer. Okay. Now, what happens is this. I said that I want to have this value. This is my new pixel value. Sorry, the old pixel value. And I want to see what is the corresponding new pixel value. So I come up to the graph, and I see that if it was this value, the new value will become this. Okay? So, and if this is the middle value, it will come in here. Can you tell me what is this function? What is this function? This one is trying to achieve. Look, this is the middle value. We understand that the middle value is a value which is not maybe very dark, not maybe very bright. So it's a middle value. So this pixel, which is in blue, is it a dark pixel or is it a bright pixel?
Bright.
It seems to be bright pixel because we are above the average. Okay? So I look at the function is given, so I look at it. This is this one, the x-axis is the old, the y-axis is the new pixels.
It's brighter.
Now, what happens is that I am transforming in here, I'm transforming into the green part, and this green one is still in the bright section, right? So what does it do? Increasing the contrast. Because we said that contrast is actually this variance. And what is variance? Variance tells me how much I am varying around mean. If variance is small, it means that lots of values are concentrated around mean. I am not going too far from mean. But if the variance is big, it means that I start to go further away from mean. So if you look at here, the pixels which are close to mean are starting to be shoot out much further away. Like look at here. It is a dark pixel, it will become darker, but what happens is that I start to go away from my mean. So it means that I'm increasing the variance, which means that I am stretching my contrast. The contrast will become bigger. So from lower contrast, I go towards the highest contrast. Now, we have a very, very famous function. Look at this one and tell me that if I give, let's say, the LENA image as an input, this grayscale LENA image as an input, what do we get as an output?
Binary.
We get a black and white image. How that happens, this value m is called threshold. Any pixel less than that threshold will become 0. Any pixel above that threshold will become 255 if it is an 8-bit image. So as a consequence, I have an image which is a black and white image. You can do it in MATLAB, you can do it in any program, you can convert your image into black and white image, and if you use something like a GIMP or Photoshop, it actually tells you what the threshold can be, so you can play with the threshold. So can you tell me that if I am choosing this function, it's a straight line. So this the green one in my new function. Can you tell me that what happens now? Still I have a binary image, but the portion which was white will become bigger. Why? Because I start to make more pixels which are white. And as you can guess is, if I have this orange color as a function, again I have a binary image, but this time the portion which is black will become higher, right? So this is a very famous transformation which converts your image into a into a black and white image, okay? Now, we have a very important graph. Again, this graph will be available for you in your note during the exam. What is very important for us is looking at this graph and being able to interpret it. So keep this in your mind. This axis is old image, and this axis is we call it new image, but we actually mean after enhancement. Okay? So x-axis is the old, before enhancement, y-axis is after enhancement. Now, how do we read this graph is this. We will talk about this graph quite a lot today, but first let's see how we can read it. How we read it is this. I will pick up a point, and then let's say I am using the nth root as a function that I want to see. Then I draw a line to here, and I see that what is the new pixel value, and I read the new pixel value. Of course, as you see, we don't have much numbers here. We have something parametric. So for us, it's important to come to this conclusion. The image will become brighter. The image will become darker. Or the image will become, I don't know, higher contrast or lower contrast. Now, here, as you can see, we have different sets of functions, and these functions are logarithmic function. Can you give me an example of a logarithmic function? What is the famous logarithmic function? Have you heard of the logarithmic function? Martin, have you heard of logarithmic functions? Very good. So the most famous one is ln, natural logarithmic, right? And we have the inverse of logarithmic function. What is the inverse of a logarithmic function, Aydun? This is called logarithmic. The inverse of this one is called exponentials. Now, if this is ln, what is the inverse of ln? E to power x. If I have the logarithm of x base n, the inverse is a to power x. They are all called exponential. These ones are called logarithmic. So the first set is called logarithmic function, which means that we have either logarithmic or inverse of logarithmic, which is exponential. Also, we have power functions. Now, we know that a power function is defined as, let's say, the constant a to power n. We use x to power n, and it's divided into two forms. If n is greater than 1, we call it power, and if n is between 0 and 1, we call it root. Most famous one, if n is equal to 2, we call it s squared. And if n is equal to 1 over 2, we call it s square root. Right? So, when we call about power function, we mean these two. Why didn't I include 1 and 0? Actually, we have 1 included. 1 is this. Where's my mouse? This is the power is equal to 1. If the power is 1, we have the identity, as you can see. And if power is equal to 0, Abdulaziz.
1.
Thank you, Abdulaziz. It's always 1. It is always 1 because a pixel to power 0 is 1, and this is not the transformation that we want. This is like take your image, clear it, and throw it away, and you put all the values to the 1. So we have the logarithmic, we have power, and for power, if the power is equal to 1, we get the identity. But basically, we can have any type of linear functions to be our transformation. There are two famous ones. One of them is the identity, and because as you can see here, we are always talking about the inverse of the function. The inverse of identity is something which is called negative. Now, if you have a black and white image, the negative is easy. All the whites will become black, all the blacks will become white. So we calculate the negative. But if the image is a grayscale image, still we can calculate the negative. But what is the consequence? If I give you an image and I tell you that I am using the negative transformation, what can you say about the output? It is negative of the image. So if the image is a dark image, I'm expecting to see a bright image. If it is a low contrast image, I'm expecting to see a higher contrast image. It's the negative of that image. We see how we can calculate it. So there are these sets of functions which are very important. We want to see how we can use these ones in order to calculate the new pixel values. We talk about the functions, but before we talk about that, let's look at this graph and do a few tests. Let me see how I can control Z?
Sorry, a question.
Yeah.
If we do a negative of an image, should the contrast stay the same?
No, not necessarily. The contrast will be changed. Because let's say 256 should be minus my values, right?
Yes.
And let's say I have 4 values, and they are all here: 128, 127, 126, and 129. if I subtract 256 from this, what do I get? I will get 129 minus, okay, yes, the contrast won't be changed. Yes.
The range always stays the same.
But the illumination, the brightness will be changed.
I agree.
One other thing that will be changed that we can say about the image is if the image does not have very visible parts inside itself, if you calculate the inverse of that, those not visible things will start to become visible in general. That is the reason that we are doing the subtraction or using the negative. And we do an example of that one for medical images when you are doing this mammography. For a doctor, in order to see whether there is a cancer or not, they have to find the subtract of the image. But you are right about the yes, about the contrast. Okay, now let's do a few tests. I have an image, okay, and this image that I have, I am using, let's say, exponential transformation. And Ulrich will tell me what do I expect to happen to the image if I am using an exponential, which is an inverse logarithmic. It's going to be darker. How do we understand it? Let's say a value which was 128. Look at here, Abdulaziz. The new pixel value is less, much less. Let's say it will be 20 or it will be 30. So 100 goes to 30. So, and if I have an image which is, let's say, 190, it will come, let's say, around 70. So lots of high pixel values started to track to be lower. So it means that the image that I have will become darker. So when do I need to use this type of transformation?
Sorry?
Sorry?
High brightness.
If I have a bright image, I mean a space image is one alternative, but if it is a bright image of the space, like if you take an image of the sun, which majority of it is high contrast, we will use it. In other high brightness, we will use it. So if we have a very bright image, in order to break it down to like mild it down, in order to become a bit darker, we use the inverse logarithm. So, Ozan, I have an image and I am using this time an identity transformation. This is a dark image. Imagine, and I'm using identity transformation. What do I expect to see as an output?
Nothing changed.
Nothing will be changed. I will get the same image. And Abdulaziz, I had an image, I took an image of the classroom, and I applied the logarithmic, let's say nth root transformation. What will happen to the image?
The contrast will increase.
The contrast will increase. What about the brightness? What happens to the brightness?
Also
It increases because, for example, let's look at here. When it is L over 4, L over 4 will be pushed up towards L over 2, right? Or if the value is smaller, let's say if the pixel value is 2 or 3, we will see that it will go to 20. So it means that the darker image will become brighter. Now, Martin, I have an image and I am applying not only nth root, but I apply nth root, I get one image, then I apply logarithm, I get another image. What can you say about the two outputs that I have?
Comparing the n.
Yes, comparing the output of nth root and comparing the logarithmic.
The logarithmic will be much
Yes, the logarithmic will result into a much brighter image when you compare it with the nth root. Of course, we understand it depends on the base of the logarithmic, it depends on the root that you are taking, but in general, logarithmic will make you much brighter. Now, if you have too many low pixel value like around here, we recommend to use logarithmic because it can expand those ones. Do you remember when we are using the logarithmic numbers, logarithmic transformation, when we have like lots of numbers which are very big or lots of numbers which are very small and we want to make them kind of like linearly changing, right? So what we want to do, as we understood what are each of these things are doing, what we want to do is that I want to find out how I can apply the logarithmic, how I can apply the other ones. I know I'm not tired, but we have to proceed. Remember, L, what is L? Yes, so how can I calculate it? It's 2 to the power n. So n minus 1 is 2 to the power n minus 1, which tells us maximum intensity value. And in the exam, usually I ask that we have a 3-bit image or a 4-bit image so the numbers are easy to manipulate. No matter what is the number of bit, the minimum value is always 0. Keep this one in your mind. So, we start by talking about the negative of the image. And the negative of the image means that what I do is I calculated 2n minus 1 and I subtracted the current pixels from that one. So in case of an 8-bit, whatever I have as an image, I subtract 255 or 256 from that one and I calculate the new pixel values. Now, what happens, you see that usually, although it's a very simple task, but it brings lots of benefits. As I said, if we have the images which are taken by these mammograms, in order for doctors to be able to see whether there is a cancer or not against, we will use this subtraction. It is pretty useful, a very simple task, but a very high consequence. Now, the next one is logarithmic. As I can see, two of you are already sleeping. I think it's a good time to start. Do you have any question? Do you have any question? Cool. If you have no question, we will continue our talk next week on Tuesday. We know that next week on Wednesday we don't have a class. There is no class. It's holiday in Estonia. So next week on Tuesday we will start our talk by talking about the logarithmic transformation. When these slides finish, I will give you homework 2. Homework 1 is already on. Please don't forget to do your homework. Thank you.